Okay, welcome back from lunch. First up is Aaron Romanowsky.
Hey everyone, good to see you again. As you can see, I'll be talking about dark matter variations and ultra-diffuse galaxies, a special type of dwarf galaxy. A lot of great collaborators who've made this work possible. Imang Tung is a grad student working here on photometry and spectroscopy, and I'll show various projects made possible by these collaborators. It says Arizona State, that's not right. So, I've not seen this paper discussed yet, unless I missed it at this meeting, but to me it was a nice recent review by Laura Salas et al. In Nature Astronomy this year about looking at puzzles with dwarf galaxies and if there are any challenges to lambda CDM or conventional galaxy formation. And they classified different types of observational versus theoretical challenges according to how strong the tension appeared to be. You know, the really famous one going back decades is the missing satellites problem, which they evaluate as a solved problem. I'm going to talk about a little bit about this problem, diversity of dwarf sizes, and more about the mass problems, which I'm going to kind of lump together as diversity of rotation curves and too big to fail problem. Interestingly, they call diversity of rotation curves one of the two strong points of tension currently with standard models. Before I show that, I just bring up a reminder of a plot. This is a velocity function plot of field dwarfs. It's a type of too big to fail question from Sebastião Trujillo Gomez. Anatoly Klipin presented an earlier version of this plot at this meeting years ago. And these are the observations of the dwarf galaxy velocity function, the standard lambda CDM mass function, and you put in different baryonic effects. What the claim was is that you couldn't resolve this inconsistency. Now there have been various papers that have looked at this and claimed things like observing mock observations of simulations would resolve the problem. I'm not sure this is a solved problem yet, so I'd be interested to keep looking at it. Again, this is a too big to fail problem, but these being isolated dwarf galaxies, you don't have effects that happen for satellite galaxies, which seems to have solved a lot of the problem in the local group. So I'll come back to this. The big problem here is that to get statistics for this, you have to use unresolved H1 line widths. And how to interpret that, that's the number one problem here. There was some effort to calibrate that, so I'll come back to that issue of getting away from the line widths. The size diversity problem, this is a summary plot from this review paper by Salas, where the gray squares are observations of local group dwarfs. This is the size-mass relation. And the idea is here at a fixed stellar mass, there's quite a large range of sizes from compact to very diffuse dwarfs. And it's difficult to see, but there are all these colored points in here are the different suites of simulations. And there's a range of sizes, but they all tend to be kind of right in the middle of the observed size range, and no single suite getting the full range from compact to diffuse. Sometimes they'll go on one side or the other, but not the full range. So this is still a point of tension. This is a local group, local volume region. I think the problem might get even worse when you look at clusters. This is the Fornax, say 10 to the 14 mass cluster, observed dwarf galaxies in the Fornax cluster, and a set of simulations from Trimmel Romanowsky simulations that they discuss finding UDGs in this cluster. Basically, they're all UDGs, just about. So there's this mismatch. Now, of course, dwarfs and clusters are going to be the hardest thing to resolve. So I'm not sure how much of that resolution issue is part of this, or if they're missing baryonic physics, for example. So you could solve this by, in principle, less feedback. These excess sizes. This is not just in Romanowsky C, but it's also in Nihao. For example, the sizes are on average too big. If you were somehow to dial back your feedback, fine, you could solve the problem, but that feedback seems to work to get the cores in the dark matter profiles. So do we really have freedom to tinker with that is the question. Just to quickly summarize on ultra-diffuse galaxies, these are not, I have discovery in quotes because they're not truly discovered in the sense as recognized. They've been in previous catalogs, just their importance not recognized, and they really became a big industry of studying with a dragonfly telephoto array, this nice instrument, cutting edge to look at low surface brightness objects, and They're originally not looking for dwarf galaxies, but they spotted so many of these in the Coma cluster that became a big industry to study them. There's an HST image of one of those objects. So there's one to the scale of the Andromeda Galaxy in spatial scale and a size luminosity relation. There are these ones here that are dwarf luminosity, but they have the sizes of giants, a few kiloparsecs. And just to summarize some of their observed properties, and the ones I'm most interested in are the ones that are the red sequence ones, the quiescent, typically found in groups and clusters. They seem to be spheroidal, found everywhere that we look on the average of 2 per 10 to the 13 mass halo. There are things called UDGs in the field, which are blue star-forming objects. Because they fit the criterion of sitting in the same place in the size luminosity plane, that is kind of a crude definition. It's not clear they're the same family of objects or they're related. That's kind of one of the points of study we're working on. So yeah, last week I presented 3 challenges related to UDGs. So here I'm going to talk about challenge number 4, which is the dark matter variations. Again, going back to this review paper on dwarf galaxies, the diversity of rotation curves, observed curve with NFW type profile, lots of them with cores, some of them with these super cusps, which getting that full range seems to be a challenge in hydro simulations. And this is where the UDGs start being part of the picture. So those rotation curves are from gas dynamics. Now these UDGs I talked about don't have gas, and so they're really hard low surface brightness objects to observe dynamically. But with the KCWI instrument that Chris Martin presented the other day, it's this efficient light bucket for gathering up the photons for UDGs and getting nice absorption line spectra. This is the deepest one we've done to do stellar populations, kinematics, and dynamics. Won't have time to cover the stellar populations, which are very interesting, but we have a whole series of studies of a variety of UDGs using this instrument. There's also been some work done with MUSE as well on the VLT. So in terms of dynamics, our hope was to get this ultra-long observation of this prototypical UDG called Dragonfly 44 in the Coma cluster, and just see if we can measure the dark matter halo profile. This is this heat map here. You can see by eye that it's cold in the center and warm in the outer parts. And in one dimension, it looks like this, these data points being the rising velocity dispersion profile. It goes out to about 5 kiloparsecs. Problem is that's not enough to get you to the virial radius, and you still have some room to play with things like the cusp core anisotropy, all the degrees of freedom you have here, not to mention potential triaxiality. You can't really definitively determine the halo mass. If you think that dwarfs like this have cores, then this is our best guess, over 10 to the 11 on the halo mass, but there's a large uncertainty on that. And also fairly isotropic stellar orbits. So it's going to be difficult to really definitively determine the dark matter profiles in these things. We're still working on it. If people have ideas, come talk to me. So we're starting to look at some more indirect tests, one of them having to do with globular clusters. This is a poster child for what we call a globular cluster-rich UDG. And this is in a nearby galaxy group around NGC 5846. So this has around 55 globular clusters. If you compare that to the Milky Way, it's a 1/3 the clusters of the Milky Way, but 2 orders of magnitude or more fainter object. So it's incredibly overabundant in globular clusters. Now dwarfs in general have a higher specific frequency in globulars than an L-star galaxy, but this is extreme even by dwarf standards. So the numbers are, present day stellar mass is 13% of the stellar mass is in globular clusters. And if you back that out to say that there were more clusters at formation that have dissolved or they've had mass loss from the existing clusters, then you get into probably most of the stars were formed in bound clusters in the beginning, perhaps even 100%, that this is like a pure star cluster galaxy that is kind of dissolved into a faint halo of light and these evident globular clusters. And this is one in the latest of a whole cottage industry of studying globular clusters in UDGs. There's been quite a few known now with this excess of globular clusters. So there's 2 reasons this is interesting. One is for the formation itself of the UDGs, but the other is, and star clusters for that matter. The other is using this as an indirect tracer for halo masses. So it's been fun. Years of work have looked at the numbers of globular clusters and the and dynamical measurements of individual galaxies, both populations and individual galaxies, and found that they remarkably correlate really well linearly, the globular cluster numbers or the globular cluster system mass with the halo mass across a wide range of mass scales from BCGs all the way down to dwarf galaxies. It works really well. So we can't be sure that this works with UDGs. I'll show you a little bit about that. But assuming that it works with UDGs as well, that they're no different from any other galaxy, that if you just blindly take the globular cluster numbers and turn that into halo mass, there's a fraction to use here, and it gets stellar mass. This is what you get. And this is a sample in the coma cluster. And there are various plots made like this. A lot of times they're inhomogeneous samples. So ideally, you want to do as controlled, as steady as you can. So these orange circles are UDGs, and squares, blue squares, are the normal dwarfs in the coma cluster, done with the same methods to try to take out as many systematics as possible. And what you can hopefully see is that at a fixed mass, say 10 to the 8th, the UDGs on average have more globular clusters, by a factor of a few. And this would be a standard stellar to halo average, typical stellar to halo mass relation. I know as you get to these low masses, it's particularly uncertain. Here at 10 to the 8th and above, hopefully we have a better idea of what's going on from theory. So, so if you believe these observational results in the interpretation, then that means that there's quite a few UDGs, at least in clusters, that have these more dark matter than they're supposed to have on average. We call them overmassive halos. And we want to just do what we can to check that, to say, do we have any indications from dynamics that this holds up? As I showed, we can't directly get halo mass, but we could at least get some measure of dynamical mass and try to test this. This is what we've done from a sample of cluster UDGs in the Perseus and Coma cluster. And what we're doing is getting globular cluster rich and globular cluster poor UDGs, measuring the velocity dispersions, getting dynamical masses, and just seeing, like, is there a correlation of dynamical mass and globular cluster content. Now, unfortunately, we only have a couple of these poor, globular cluster poor. The nomenclature is that means that they don't have many globular clusters. They're low numbers of globulars. And globular cluster rich means that there's lots of globulars. And there's a systematic offset between them. So this supports the idea that they are more massive halos. Okay, I mean, it could also be a difference in the halo mass profile, that these globular cluster rich ones have cusps and these ones down here have cores. It's technically possible. For us, it's more straightforward that this follows the normal globular cluster halo mass relation, and that they just have more massive halos. For reference, these curves here are from gas-rich UDGs in the field, ones I mentioned earlier that we don't know how they're related to these cluster or quenched UDGs. And they seem to match up quite well with the globular cluster poor UDGs. So this picture is emerging where you've got kind of these two basic populations of UDGs. One are these field, low surface brightness galaxies that fall into clusters and quench and form low surface brightness red and dead galaxies. But then there's this other population of dark matter rich, globular cluster rich UDGs that might be something else. Okay, so that is these massive UDGs, but I'm going to talk about something actually the opposite of that, which is a different type of UDG. This one is not technically a UDG. It's low surface brightness dwarfs in the nearby universe. When we spotted these with lots of star clusters, we thought, great, here's a really nearby one, do some detailed dynamics, understand what's going on. But the big surprise was, we thought we'd map out this massive dark matter halo, that we found the opposite. The velocity dispersion was extremely low, less than 10 kilometers per second. So the enclosed dynamical mass within a few kiloparsecs was this equal to the stellar mass, or consistent with the stellar mass. So a little room for dark matter. Now, of course, you can't prove the non-existence of dark matter here, but the best models have very little dark matter, which incidentally, it kind of argues against models like MOND, where dark matter doesn't exist, and you should always have a dynamical anomaly. So here you have a way of extracting. You can have a galaxy with no dark matter, which suggests that dark matter actually is a substance that can be extracted or lost or never there in the first place. So a lot of different possibilities to say, like, there was debate for a while about these observations, interpretation. I like to think this has pretty much been settled. Distances, we've got very deep HST observations to confirm the distance from the tip of the red giant branch. So now it's more of a question of, well, how do you explain these things, the origins, and various kind of scenarios out there. I'll talk about a few of them. One of them goes back, or before I get to the scenarios, I'll just go back to that velocity function profile I showed at the beginning. This is more updated work from Sebastian Trujillo and Gomez, now taking resolved kinematic profiles to sort of get it away from line widths. And there's more and more of observations of mostly H1 kinematics and putting on a plot of stellar to halo mass. And here's a standard relation. And what he was pointing out is that there's this tail, apparent tail to low halo masses at fixed stellar mass. And those two galaxies I just showed, DF2 and DF4, are over here. But there's also these field UDGs that have been studied with H1 kinematics that are finding similar offsets. So the idea is that you have some scatter expected in the stellar to halo mass relation, but perhaps not that much scatter that we're observing their order of magnitude. And I'll just say the globular cluster rich UDGs that I showed earlier, those would sit on this side of the relation. So we're seeing this very large scatter in UDG dynamical masses. Okay, so probably the most standard explanation for how do you get these depleted dark matter dwarfs, and there's been a bunch of papers about this now. This is one of the latest using the fire simulation in a cosmological context to say that as you drop a dwarf galaxy into a larger galaxy, it gets disrupted, strip the dark matter first, you start stripping the stars. Before it completely disrupts, you basically have no dark matter. So this is a mass with time, and here the dark matter has dropped off after a couple of orbits. This particular one is in a sweet spot where it's long-lived, and basically the total mass is the stellar mass. So you can, by gravitational tides effectively, you can pull out the dark matter and be left with just a pure stellar galaxy. Now, interestingly in this model, the prediction is then that this happens all the time, that if you take a massive elliptical galaxy, for example, about 1 in 3 times they'll have at least one of these dark matter poor dwarfs. So it's a really common phenomenon, and then it would be the expectation is, well, we just haven't seen this because we haven't done these dynamical measurements until now because it's too difficult. But the other thing that does concern me about this simulation is that all the pictures, almost all of them, seem to show tidal tails. There's been a lot of deep work observationally on these particular galaxies that don't show anything like this. There are some perturbations in the outer parts, and there's some discussion of exactly what that means, but not this very dramatic tidal tails. Okay, well, another part of the puzzle of these galaxies are unusual, not just in being dark matter depleted, but also in being having unusual population of star clusters. These things that we call globular clusters initially, when you look at their sizes in detail with HST and their luminosities, first of all, they're very luminous. So this filled histogram are the two galaxies, star clusters combined, and this open red histogram is the Milky Way luminosity functions. So they're missing all like the normal ones. They've just got these all like omega Cyn type luminous star clusters. And omega Cyn in the Milky Way is thought to be a strip nucleus. So also they have very large half-light radii, large ellipticities. So that's like a bunch of these big luminous star clusters, which is another anomaly. They're old and metal poor from spectroscopy. So then the question is, whatever scenario you want to explain these galaxies, you need to explain their star clusters at the same time. And ideally have it not be a coincidence, but that they're somehow causally related, that there's not two separate phenomena going on that are strange in the same galaxies. So here's a model from Sebastian Trujillo Gomez that does this sort of scenario, which is based on sort of these empirically based star cluster formation evolution models, also working with Dietrich Clausen, where they postulate that these galaxies formed at early collapse times, where you sort of have a runaway effect if you have very high gas densities. And this is this flow chart that starts here, high concentration, high early collapse halos. Then that leads you to initially high stellar mass fraction to begin with, but then all these other effects take place where you've got more star formation in massive clusters, which then in turn creates more feedback and expands the galaxy more and could create these observed systems today. And so this is their mass models where the initial dark matter profile is this dashed one, and after they include sort of all these effects, including the feedback, you get the dark matter down here. So it's not that there's no dark matter, but that it's partially started off with a little bit low in the first place and partially been pushed to larger radii, say below 10 kiloparsecs, where we're not observing. Thanks. And then if you make this plot I showed before of stellar to halo mass, the idea is that these circles here are the actual halo masses, but then if you observe those and do these standard fits that don't take this extreme feedback into account, then you push things over here and you infer an anomalously small halo mass. So their claim is that these are not actually overall have low halo masses. It's just that they've got this extreme feedback, mainly that push the dark matter into an extreme core. And that it's intimately related with these weird star clusters, that those are what created that extreme feedback. So I'm going to show a final model, which is the one our group favors at the moment, which is why in any of these explanations, out of all the places in the universe it's been found, that there's two in the same group in the same place, okay? And it's sort of like, does lightning just strike twice? That particular group got lucky and got two of these, or is it because they are somehow causally connected? And this is called the bullet dwarf scenario, and you've heard of the bullet cluster. The idea is you just have an unusually high-speed collision where the gas is collisional, the dark matter is not, and the dark matter carries on, and if you have enough of a head-on collision, then the gas just stops in its tracks, gets shocked, forms stars and star clusters, and you get left behind with these dark matter-free galaxies, and then you have to also be in just the right position with respect to any central galaxy that they don't get disrupted with time, because not having dark matter, these are not very well protected from tides, but if they're far enough out, you're okay, and they stay there for a Hubble time. And interesting, and this was first Joe Silk came up with this picture, and one of the nice parts of this picture is that it not only explains the lack of dark matter, but also the star clusters. Because of these extreme high pressures created by the collision, you could have more massive gas clouds and more massive clusters that are formed. So it kind of all holds together. Now there's simulations from Shin and Lee that have done this in more detail, and one of the possible predictions that comes out of this is that it's not just those two dark matter-free galaxies, but there could be a whole trail of dwarfs left behind, including the initial dwarfs that had their own stars that are collisionless, and those could be at the end of this trail with high dark matter dominance. That's the opposite of the dark matter poor galaxies. So one of the first things that we did, or Peter van Dalkum did, is then look at the positions of galaxies in this group of dwarf galaxies and just see, is there any evidence for a trail? And you can kind of see by eye, hopefully, that there is this line here that just happens to line up with the two dwarf galaxies that have the low dark matter content. So there's 9 plus or minus 2. We did various statistical analyses to check that this is a significant feature. So we're doing follow-up work now to say, like, okay, well, how can we test this prediction? Now, the nice thing about this, it could be completely wrong, but it is testable. There's a lot of predictions you can make about things like the velocities are almost linear along this, the distances are almost linear along this track. These are all things that we're trying to test. The stellar populations is one big part of it. If you have two galaxies that formed at the same time, they should basically have the same stellar populations. One way we've done this so far is doing SCD fitting from the optical to the near infrared using Prospector to get out the ages and metallicities. And here's the results. With that kind of, that kind of data, your error bars are going to be large, but they are at least consistent. The stars in those two are, this one and this one, basically they're right on top of each other in this plot. Large error bars, at least it's a consistency check that they seem to have the same stellar populations in age and metallicity. Now the globular clusters and the one that's been measured, this is from Muse spectroscopy, they have a same age consistent with lower metallicity, and there is some expectation from the models that the globular clusters form first, so they're more metal poor, and there is some enrichment of the stars as time, over less than a gigayear during the collision process. Whether that works out quantitatively or not remains to be seen. So the next consistency check is looking at the comparing the globular clusters. The idea is that these clusters are all formed in a single starburst together in both galaxies. They should all have basically identical ages and metallicities. We've tried to look at the individual spectroscopy of those. They're too faint for that, but you can use the colors as the next best thing. It's a consistency check to see if they all have the same colors. So this is a plot of colors of globular clusters versus galaxy mass. This gray region is Virgo dwarf galaxies, as well-established relations on what kind of colors their globulars have and the luminosities. And so what you see, these are the observations of these dark matter poor galaxies. The globular clusters are unusually luminous, as I showed, but they also have a very narrow scatter in clusters and colors. And so this can be quantified as a sigma color here. This is the cluster color scatter versus number of globular clusters. And these are observations of Virgo dwarfs. And say for down here, they're typically of say 0.1 dex color scatter. These things are down here at the level of 0.01 magnitudes of color scatter, at the level where you're starting to worry about stochasticity from red giant branches stars. So this supports this picture that they're coeval clusters, and which again would support this trail of galaxies, bullet dwarf scenario. So there might be some other scenario that explains that, but that's become a fundamental observation that you need to explain for this system. So it passes this falsification test. We're working on more tests. Stay tuned. By next year, we should have more. I've not seen any other scenario that predicts various observations about these globular cluster colors and luminosity function. So I'll just wrap this up by saying, blast from the past, that UDGs are not nearly normal galaxies. Make that claim. There seems to be a subset of UDGs with these anomalously populous globular cluster systems that look like they could be what we call failed galaxies. What that means is something that still needs elaborating. An opposite population of low dark matter content, where I think the only thing so far that explains all the observations is this bullet dwarf scenario. So thanks for your attention, and I appreciate more questions or comments.
Thank you, Aaron. We have time for a few questions while Eve, the next speaker, is set up. And I'd like to encourage, in particular, questions from the more junior members of our audience, if you have any.
Hi, Aaron. Great talk. So I had a question about the UDGs with populous globular clusters, for example, UDG1. Has there been any study looking at the distribution of these globular clusters, the spatial distribution, whether there is any overdensity towards the center or like?
Yeah, that's what's interesting is the density profiles of globular clusters, there's not a huge amount of work done so far, but on average they seem to be similar or more compact than the stars, which is opposite to what you find in normal dwarf ellipticals, where they tend to be more extended. They seem like a halo population, even if they're not necessarily accreted in the way a halo would be. So this is different. They're more centrally concentrated, which seems to, well, two things. One is it doesn't look like they're just a normal dwarf that expanded, because you would expect it to expand self-similarly. You know, the globulars go farther out, the stars go farther out in lockstep. But the other is that this maybe supports this idea that they formed in a central starburst, the globulars did, which maybe helped puff up the galaxy.
A comment on the tidal tail of observed galaxies. You mentioned that we didn't observe that much tidal tails, right? I'm thinking that maybe it is not necessary to must have tidal tails. You can imagine that the dark matter is stripped while the galaxy, the stars in the center, has not much affected by the tail yet. At that stage, you won't expect tidal tails. So it really depends on the initial configuration of the system, how compact of the stellar component and the dark matter component.
Well, I think, I mean, someone maybe could look at how robust this is, but I think the idea is that once you get to the point of stripping out almost all the dark matter from the central parts of the galaxy, it's difficult to not strip out the stars at that point and not see tidal tails. But you know, if someone wants to study that systematically to check, that would be good. I also was a little bit simplistic about this idea of not showing tidal tails. I mean, if they are dark matter free, you do expect to see some hints of extra-tidal stars. It depends on how close you are to the big galaxy, and we've got some line of sight distances that shows that probably, at least one of them is not that close, so maybe you don't expect to see extra-tidal stars in the first place at a big level.
Hi, thanks. About this scenario where you form all these globulars in the collision, and therefore obviously they're very abundant, but also presumably in this model that's why they're so much more massive. I find that a little confusing, because presumably over the whole population of galaxies, many globulars formed at very high redshift, where number one, the overall gas densities and pressures were significantly higher, and you also had a lot of mergers. So wouldn't we also expect to see, just in random galaxies, many globular clusters of that same mass and luminosity? Or is it just that these lacked the Hubble time of evolution that caused them to lose mass? Or what's going on there?
Yeah, it's a good question, and it kind of raises the question of why don't we see more diversity in globular cluster systems in general? I mean, what I showed, there's these patterns that are like really constant luminosity functions from dwarfs to giants, and why don't we see more diversity in the first place because of all those histories? I think different histories is a good question. I mean, just off the cuff, I would say that, you know, maybe the difference is those galaxies you mentioned in the normal formation history, they've had lots of times for tidal shocks to kind of wipe out a lot of the clusters or reduce their masses or something. These are different because they've been basically isolated. They had one formation event and then nothing happens. And that allows them to preserve those initial large sizes and masses.
Okay, let's thank Aaron again.